audio. It's the right audio.
You're not sharing screen yet.
Oh, yeah.
Hey, nice to see you again.
Good to see you.
Yeah,
You're going to present?
yes, I'm gonna
nice.
present. Yeah,
So-
I have seen Marius Bedrunka
yeah.
presentation just
just
now.
now, yeah.
Yeah,
Did you like it?
yeah, sure. It was very interesting, and we should discuss definitely.
Yeah.
Right. I have replied your email. I have.
Yeah.
All right.
I didn't get it yet because I was in Poland for holidays.
All right. No worries.
I left Lisbon.
Uh-huh.
Straight I went to holiday.
All
I
right.
just came
Okay.
back.
Okay. Okay.
But after we should definitely. I can introduce you to Mario.
All right. Okay. Okay. That should be nice. Yeah. Okay. See ya.
Okay.
But just to check, I pronounce all three of the E's in your name.
Mm.
Yes,
Louis Hegeli.
that's what I was going to do.
Yeah. Fine.
Yeah. Sometimes you need to know which language it comes from.
Yeah, from Louis from Portuguese and Hegeli from Germany.
Yeah, but they said it French, so you lose one of the E's.
Possibly.
Yeah.
Yeah.
I guess everyone's wondering, I decided we just give people a few minutes to drift back. That would be like.
Just a small trimming at the last minute. Just a small trimming at the last minute.
Final details.
Yeah, one of the names of the co-authors was wrong. The one who is not here, but yeah. Anyways,
We can start if you want.
yeah, sure.
So welcome back for this last session today. We have started to talk by Louis Hegeli and also with Paolo Filippi and their colleagues about the analysis of the Stokes hypothesis and the lattice Dawson method.
Okay, Paul, thanks for the presentation. So my name is Luis Hegeli, and with my coworkers, Ricardo Bazarin, which is here, Diogo Zibert, and not here physically at this room, but he will probably will be here in a couple of minutes. Myself, Luis Hegeli, and Professor Paulo Filippi. I'm going to present this analysis of the Stokes hypothesis within the lattice Boltzmann framework. So the summary of my presentation is a motivation, and then I'm going to talk about the model and jump into applications for this model. So my main motivation for this model is to apply it for jets, for one single phase jet and also multi-component jets. Some years ago, in 2010, there was a huge oil spill in Gulf of Mexico at the Macondo field, and it was very well known by the people at the time. So we want to know the destiny of the oil spill, and if you model this kind of a oil leakage, you're going to know how to deal and to make plans and contingency plans in order to make a better and safe operation and environment. So we want to especially then make this model of the subsea oil jet in a lab. So we're going to transfer the jet to the lab. So this is in the left-hand side, you can see a jet, oil jet in a super controlled environment. And we want to especially make the measurements of the dispersion of the droplets, oil droplets inside the water. So first, we want to have this no artificial dispersion, so a pure jet. And then we want to have two types of dispersions. The chemical dispersions, where we're going to add surfactants to the jet, to the oil. And the other one, which is a mechanical jet, where you're going to just simply impinge water jet into the oil jet. So with this, we can see that there's a need of a single and multi-component flow models with high accuracy and high numerical stability. So for our model, we want to study for these Newtonian fluids. We have this relation for the viscous stress tensor between the first viscosity coefficient, which is then just in the factor of the strain tensor, and then the second viscosity coefficient, which is simply multiplying the divergence of the velocity. The Stokes hypothesis requires that viscous stress tensor should be traceless. That is, there is a relation between the first and the second viscosity coefficients. Ladd in 1991 introduced a true relaxation time model like this. Do I have a pointer? Oh, yes, a physical one. Yeah. So this is a model introduced by Ladd in his seminal paper in 1991, and so we have these two relaxation frequencies, and these lambdas are then related to the shear and bulk viscosities. We're gonna investigate the Stokes hypothesis with a single relaxation time model. So we use, as usual, in our group, the Lattice-Boltzmann equation, the Lattice-Boltzmann method, with a single relaxation time. And this is the relaxation time, tau, which will give you the relation to the viscosity. We also have the hydrodynamic variables, the density here, and the momentum here, or u, the velocity. So given as a sum of the particle distribution function f. The pressure is related to the density, but we don't care about the density since we are only solving for the pressure. So we care about the pressure. And this is the viscosity. The viscosity is related to the viscosity to the relaxation time. AS is the scaling factor. In our simulations, we are using the D3Q19 model and the D2Q9 model. Both very simple second-order stencils, very well known inside the community. So this is something that is becoming more and more common here, and I really like this motto of the Lattice-Boltzmann. The collision is local and nonlinear, so we have a couple, we have a distribution, then we perform, we have the equilibrium distribution, and then we make a simple collision, and we came up with this nonlinear collision, a local collision. We have a redistributed set of populations, and the streaming of the particle distribution is non-local but linear. All right, We also, for the Maxwellian distribution function, as we also are using a simply second order expansion of the Maxwellian distribution function, where we have the first order moment, the second order moment, the velocity, and the first order moment, the velocity, and the second order moment, the square of the velocity. H2 is simply the tensorial Hermite polynomial of second order. All right. Our model is like this. Then we have the evolution equation written in this manner here with the equilibrium distribution and the non-equilibrium distribution. We have the regularization procedure, simply where we state that there is the regularization with rho, and GI is or either the original distribution that is incoming to the site, Fi, or the regularized distribution, Fi hat, which is the regularized particle distribution. So here we have the set of the tensorial Hermite polynomials, and here we have the moments. So, for example, in 2D, we're going to have 1 plus 2 plus 3 moments, 6 moments, and in 3D, we're going to have 1 plus 3 plus 6, so 10 moments in 3D, 3 dimensions. The model is here. We have a corrected second order tensor. This is the tensor that we evaluate simply at the site, and this is the corrected second order tensor. This is, as you can see, the deviatoric part. So it's the traceless part of is a traceless tensor. And then after this, we perform the regularized distribution function like this, inserting this guy here into the evolution equation. And this is simply our method. We also are using regularized boundary conditions. We have several closure equations for these conditions for each moments. For example, if you take Dirichlet boundary conditions for velocities, you're only going to need equations for the density, or this equation here for mass conservation, and equations for second order moments. Here I'm showing you equations for density and second order moments, since, for example, for the Dirichlet boundary conditions, we don't need to use any kind of equations for the velocity, since they are already known, which is super. Let's say it's obvious, but now we're stating that. Okay. So here we are summing in a subset of velocities. We are summing a subset of velocities, incoming velocities to the site at the boundary and outgoing velocities from the site. What are the incoming and outgoing sets? So the I set is the set of populations incoming to the site. For example, this is a flat wall, and these are the distributions that are incoming to the site, and these are then the distributions that are outgoing from the site. Okay, so these are the definitions of the set of populations. Our regularized boundary conditions, also we can add some very tiny, very specific details. For example, at a plane wall, at a constant x, and every derivative of the velocity of every velocity with respect to x should be 0. And then we can impose this condition here at the given moment, since we know now the derivative of this given velocity. So we are imposing locally the derivative of the velocity at the wall. So now some applications. This is the double periodic shear layer flow. We have simulated for several Reynolds numbers, and also for several resolutions for 32 square, 96, 288, and 864. And we have measured some quantities. For example, the rates of convergence. We are comparing to the plain BGK, so the straight implementation of BGK. We are comparing to the work of regularized lattice Boltzmann based on the work of Lat and Chopard from 2006, and we are also comparing our results here. And these occasion results, we keep the rates of convergence for Reynolds 4,000, 15,000, and 30,000. This is for the rate of convergence for this problem. For the compressibility effects, we can measure this based on the divergence of the velocity, of the norm of the divergence of the velocity. And for several Mach numbers, now we are, if just an example, if you keep the Reynolds number, let's say high for 30,000, you can get a very good results here, always diminishing the error regarding to BGK and also from the regularized, which we are calling here Lat, right? But it's the regularized version of it. So we are comparing all of these, and for different lattice sizes here, for starting with 33 and finishing with 513. Another comparison is the lead-driven cavity flow. This is a very is an homogeneous flow with a lead-driven lead that will drive the flow from the top, and the box is closed with all the velocities zero. So there's a impermeability condition at every wall, and so this is the setup. And this is a slightly different version of this model, but we are using it. And so we are comparing this for example, Reynolds 10,000, and we are having a very good results regarding to the experimental work of Prasad and Kozev from 1989. This is for the average velocity, and this is for the fluctuating velocity, for the cross velocity, and also for the UX, root mean square, and Y. And we are getting let's say the trend. We are failing a bit here, but the trend is in a very good position, is in a very good situation. So these are our results. We are also showing some numerical stability tests for the lead-driven cavity. This is for Mach 0.2 and a little bit more than that. So this is our results for the stochastic moment-based method. So we are here in kind of a million Reynolds number. This is, let's say, for the numerical standpoint of view, it's a very good one. We are not talking now about physics. We're just talking about numerics. And this is, let's say, one order of magnitude and after the second here, which is the work of our group as well. And these are works just explaining. This is Mohammed and Reis, and this work is from Lat. This is the regularized version of the lattice Boltzmann. So these are some just pictures, just some movies here that we are simulating for the lead-driven cavity flow. Oops. So this is Reynolds 20,000, and we can almost see this is the velocity magnitude. So some turbulence now is spreading much more than the Reynolds 10,000 on your left, which is not appearing. Okay. Right. Yes. So this is Reynolds 10,000, which was we thought it was super turbulent some years ago, but now we can see that we are simulating Reynolds 20,000, 30,000, even 100,000, and now we are seeing that this Reynolds 10,000 is only turbulent in a tiny part of the cavity. So the Reynolds between 20 and 30,000, the turbulence is much more. There's a there's a kind of a transition between these two Reynolds number inside the cavity. We can see this now. So another application is for jet. This is our main goal. So this is for the single fluid jet. So this is the results from Hussein. We still have some problems here with the boundary conditions at the outlet because of the counterflow, but we're still, this is a work in progress, but we are getting let's say the self-similarity profile of this jet, and we have gotten also the good experimental P factor when you're measuring within the center line of the profile, and this is also a video here for our jet. So for Reynolds 15,000, which the Reynolds number doesn't matter that much because after it becomes turbulent, it's self-similar. And just as a closure for our applications or for the talk, this was just published yesterday. So this is also we have been using our correction here, and this is the Laplace law for the multi-component lattice Boltzmann. So this is the work performed especially by Ricardo Bazarin, which is here, our co-worker, co-author, and we are simulating here very different viscosity ratios from a range of several decades, and we are getting the Laplace law for these viscosity ratios and for several interfacial tensions as well. So these are results, and we invite you to read that paper that was just published yesterday. So as a conclusions, then we have enforced the Stokes hypothesis with only one single relaxation time, only using BGK. And so BGK models can fulfill this hypothesis if we apply this correction within the viscous stress tensor suggested also by lab. The effects of these corrections, then we have investigated accuracy, rates of convergence, numerical stability, compressibility effects, and we are getting very good results, maintaining the computational costs. And we have then improvements in accuracy and stability with no compromise in the rate of convergence for these cases that we have studied. So with that, I thank you. I let this and I'm open to questions.
You were talking about the pressure, because you will look into the data again, the pressure.
Not. Thanks very much, Matthias, for the question. We have compared the results for pressure, but not the rate of convergence for pressure. But this is a very good suggestion. We'll take that into. I think we're gonna have some good expectation from this, because now we are setting the tensor, the wall stress tensor, in a very precise way at the wall. So the wall usually at the wall there's a mess if you don't perform any kind of a modification at the tensor. But if you add some correction at the tensor at the wall, then the function becomes smoother. So I expect to be to have more accuracy in the pressure results as well. Thank you.
That so-called model is the original second order regularized model that they proposed.
Yes, the one with high dissipation. Yes.
You say that the torsion regularized is more stable than the original second order regularized lecture part. And here in your comparisons, it was like significantly less stable.
I don't I don't know exactly if this is the recursive regularized lattice Boltzmann. Is this Malaspina's? No, it's the boundary condition. It's not the high order. It's not the. Yeah, I'm sorry, not putting the right reference. Sorry.
And if that's time, move on. So, Lewis, thanks again.
Thank you.
Kannst du ihn nutzen?
Yeah, very good.
So next up we have Maximilian Diller and colleagues talking to us about interaction of system and model parameters in LBM simulations of a stationary cycle or something. So, all yours.
Yeah, thank you for the nice introduction. Today I want to talk a bit about a master's project I did. I'm a master's student at the University of Applied Science in St. Augustine near Bonn in Germany. And now this project sneaked itself onto the conference floor here. Let's start with a very simple cylinder flow again. I'm sure a lot of you have seen it even today. And from this, we can extract some exemplary observables. In this case, let's say the coefficient of drag, which can easily be calculated from the force acting on the cylinder by the fluid. If we look at some literature values over time, so it's here the coefficient of drag over the year, publications, the left two clusters are experimental values and the rest is numerical data. That is often referenced for several Reynolds numbers. We can both see there's quite some variance in results for the same Reynolds number. And recently there has been more data acquired. I mean, there's obviously some advancement in CFD, so it gets easier to get data, but there's not necessarily more agreement in the data. And today I want to go over some reasons why this comes to be, both from a numerical standpoint, so looking at solver parameters being, for example, the solver itself, in our case, the open source Lattice LBM framework, the collision operator, algorithms like the boundary condition, the resolution, etc. And on the system side of things, the domain dimensions, the cylinder size, the Reynolds numbers, things that are purely physical and not dependent on the LBM by itself. Starting with the system, we have a circular cylinder placed at half height in this rectangular domain, both in 2D and 3D. We have several boundary conditions. We have a constant velocity inlet, a constant pressure outlet, and apart from that, everything is periodic boundary conditions to make it easy. The Reynolds number we will be looking at is mostly low Reynolds numbers between a Reynolds number of 10 and 300, but I also brought some exemplary results for a Reynolds number of 3,900, which is a little bit more turbulent and commonly used. For nomenclature, I took the characteristic length, which is the cylinder diameter, and call it grid points per diameter as both the characteristic length in lattice units and the resolution, so a measure for a resolution. This will come up later. And all the system dimensions are then related to the cylinder size in how many cylinders will fit in the respective direction. So diameters per X, per Y, per Z. I think that makes sense. Again, the circular cylinder, a very well-known benchmark. Quick reminder for everyone who's not working with solid bodies in the LBM. Above the solely theoretical case of Reynolds number of 0, which has an analytic solution, there exists the stable and stationary flow with two opposing vortices behind the cylinder, which is symmetric. And above a Reynolds number of around 47 to 46, periodic vortex shedding sets in after any perturbation, which then leads to this characteristic Van Karman vortex street, which you've also maybe seen today. And after that, depending on which sources you ask, between a Reynolds number of 150 and 300, we observe it at 200, but I will come to that later. An intrinsic three-dimensionality in the flow starts over, and you need 3D simulation because much more turbulence occurs, and that needs needs the third dimension in simulation. In this case, I will bring you 2D simulation up to a Reynolds number of 200 and 3D simulation above. Again, some of the parameters I varied on the numerical side is the bounce-back boundary condition algorithm, so the solid boundary condition algorithm, having both the simple bounce-back boundary algorithms, the full-way and the halfway bounce-back algorithm, which depict the boundary as laying exactly or approximately halfway between the last fluid and the first solid node around the boundary condition. And as a more elaborate version, I took in the interpolated bounce-back boundary condition in its linear form, which interpolates the bounce populations from two fluid nodes, recreating the exact or more exact location of the boundary condition. Which observables did we measure? Like I told you before, I looked at the drag coefficient. And if we look at drag coefficients, we can as easily look at the lift coefficients. Both force coefficients are calculated from the forces acting on the cylinder in flow and cross-flow direction and normalized by the flow characteristics being the density, the characteristic velocity, and the characteristic length in the flow. As a time series, they look somewhat like this after an initial settling period. By the way, in blue is the drag coefficient, in orange is the lift coefficient. We reach some kind of an equilibrated state from where then the vortex shedding starts in a very periodic and ordered manner, where we reach converged state here where periodic vortex shedding is occurring. And from this, then we can extract the mean drag coefficient as a simple scalar observable, which is often compared in literature, and the amplitude of the lift coefficient. So much for the theory. Now comes a lot of data and plots. So beware of colors and data. First of all, we want to look at one of the most fundamental parameters in numerical simulation, which is, of course, the resolution. In this case, I brought you the coefficient of drag and the coefficient of lift for a Reynolds number of 200 in the 2D simulation, and did a lot of simulations for very different resolutions, and also varying the parameters I told you about before, being both the boundary conditions. In this case, you see the full-way bounce back being depicted in blue, halfway bounce back in orange, and interpolated bounce back in green. And the collision operator, dots represent the standard BGK model you've heard before, and X's do correspond to the Swiss-made KBC collision operator. Yes, I also included some very high resolution converged states here as a reference, and the literature values I also showed you over time before as little red markers on the right side. And in short, we can see everything does somewhat converge in this quite large range of literature values, but we do see quite a variance in the beginning at lower resolution, and this is a very non-monotonous convergence, obviously. If we now look at literature and convergence studies, and I'm sure a lot of you have done convergence studies over grid resolution in the past, you might recognize, okay, they often look somewhat like this. You have some, maybe 2, 3, 4, maybe 10 resolution values that are quite equally spaced. In this case, we see if we arbitrarily have chosen these values, see a very nice monotonous convergence, say, okay, we are converged somewhere here, they are quite equal. But you also might see these, which are equally spaced, but just like a couple of grid points different. And okay, we still have convergence, like the variance gets lower over the resolution, but you can already recognize that this convergence is non-monotonous. Or by being unlucky, we could even, in a similar spacing, get these values and think, okay, we are converged from the beginning on. There is no improvement with a higher resolution. So what to take away from all these data points? don't trust too coarse convergence studies and maybe invest one or more simulations into really understanding the behavior of the parameters. Now, why don't we just resolve everything as high as we can? Well, yes, in 2D, that's obviously possible. We have a lot of hardware right now, and we can just simulate at a very high resolution, and then everything fits well within the range of literature values. So here we have both the halfway bounce-back boundary condition and interpolated bounce-back boundary condition, who become quite similar at this resolution and fit in all the literature values. I also added some more experimental values that I extracted from graphs before, and this looks quite nice, right? But this is Reynolds number 200, or up to a Reynolds number of 300, and we are still in 2D. And obviously today we always want to have the option to simulate in 3D if there are 3D effects. And as I told you earlier, at higher Reynolds numbers, which we will come to now, this will play a role. In this case, I simulated a couple of Reynolds numbers from Reynolds number 100 to 300 in 2D. And you can see a very smooth trend from the low Reynolds numbers to the higher Reynolds numbers, both in the settling period and in the converged state. If we now compare this to a 3D simulation at Reynolds number 200, we see almost identical values. So they are overlaid for both boundary conditions, being the halfway and the interpolated bounce back. And you can see here on the left, it's the 2D, here's the 3D values. They are practically identical, which legitimates our 2D simulations below Reynolds 200, obviously. But if we now look at simulations with higher Reynolds numbers than 200, this starts to happen. So here in the Reynolds 200, the dark blue one, we still have this simple converged state. By the way, here the observed time frame is 10 times higher. This is why we see so much more of it. And then above 200, the magic starts to happen. Everything becomes more chaotic, more complex. The flow behavior, also if you look at it in 3D, gets way more complex and, let's say, interesting. So in this case, if we still want to extract these scalar simple observable values, this gets more complicated as well, because you in the blue case, you can maybe say, okay, it's somewhat converged, but where does this converge? This converges somewhere here in this semi-periodic state, but everything gets more complicated. That's basically what I want to say. On the right, I've also plotted the 2D values, which show this smooth trend of the Reynolds number. And I also included as axis the 3D values, which if you extract it from these pictures, then show a divergence from this, which also corresponds to literature and gets this less smooth trend here. So what to take from this again, 3D simulation becomes necessary. So we do need this more computation power to reach it. So we can't have these high resolutions as I showed you before in 2D. As promised, also some results for a higher Reynolds number. Now we push the Reynolds number up one order of magnitude again at Reynolds number 3900, which is like still for some a low Reynolds number, but which is way more turbulent. The picture differentiates even more. In this case, I also had to use, I couldn't use the standard BGK model because it crashed. And I, instead of it, I included the regularized BGK model, which is more stable because of the dissipation, and compared it to the KBC. And we see both the collision operator, left to right, and the boundary conditions marked by the colors again, the full way, halfway, and interpolated bounce back, diverging from each other. In this case, some results are quite near to the literature. For example, the interpolated bounce back boundary condition here, fitting into fitting this literature value quite well. The full way bounce back here with the regularized, or here with the KBC, being somewhat near the literature, and halfway bounce back just oscillating all over the place, being chaotic and not usable at all. Which, if you remember, before full way and halfway almost showed very identical pictures below Reynolds number of 200. So in this case, the higher the Reynolds number, the more critical every parameter choice gets, not only the resolution, because this is not resolution dependent here. This is the boundary conditions and the collision operators. Now, I showed you a lot of drag coefficient values. I also have lift coefficient and Stroll numbers, but just to keep it short in this 15-minute time frame. Some of you might want to look at some more turbulent observables, and this is what I also did as a small outlook. I included some average velocity and average Reynolds stress profiles at these common 3 locations behind the cylinder, being both averaged over time and over the 3rd dimension, so in the Z direction. If we look at these, in this case with the interpolated bounce back and KBC collision operator, this combination gave the best results. You still see a lot of variation. Some results seem to be converging monotonously. If we look at the first velocity profile on the left in stream direction, we go from a bathtub-shaped profile at the lower resolution to a more V-shaped and physical profile at higher resolution. But if we look at different profiles here, it jumps all over the place. Here it jumps quite a bit. And if you look at the cross-stream velocity, we also have outliers here, outliers and jumping here. So in this case, if we look at a single result, it might look okay. If we look at this convergence trend, which is indeed not converged at all, we get a very different picture. If you compare it to literature again with the highest resolution, which is at our hardware limit basically with 1 GPU, some results again look very nice. Velocity profile, this okay, somewhat nice. I mean, some literature is also a bit unsure if it's 0, if it's there, sorry. But for the Reynolds stress on the right side, for example, here we have these edges in the profile. So this is not very nice to have at this point. To conclude everything, the essence of my talk should be to motivate everyone to look at every parameter and do at least some sort of detailed parameter analysis and check the behavior of your system, of everything that you use and every dial you can turn to understand what it does in this case. And this gets even more difficult if you are working with 3D, of course, because you are computationally more limited, and at higher Reynolds number because the influence of every parameter gets way harder to, way more severe. So thank you for your attention, and if there are any questions I left open, I will be happy to try answering them.
About your convergence strategy. So you always increase the number, I mean,
This one?
Linearly, yeah?
Yes.
So in a convergence study, you should increase the number of grid points exponentially. Otherwise, I wouldn't call it a convergence study. I mean, it also makes it difficult to actually compute the order of convergence. If you have an exponential increase in resolution, then you can easily compute the what is called the empirical order of convergence. Yeah?
That's true. If we take like 10 grid points here and then 100 grid points as one order of magnitude higher, we lose all of this, and maybe somebody simulates here and says, okay, this is pretty nice, and
They don't convergence study if you just increase linearly your resolution, then you're not doing a convergence study. And then obviously you run into your problem that you're pointing out, that the the numerical noise is larger than your signal of your convergence. I mean, this is what you're showing. Yeah, this is your entire point.
Yes.
That this doesn't work.
Yes.
Yeah. So if people do it that way, then they are not doing a convergence study.
Okay, but
Yeah.
they call it a convergence study. So I also call it a convergence study.
So I don't think that's
I think that the problem here is that there is no true solution to dragging this coefficient. So performing the convergence study would be difficult because what difference are we measuring? Right?
What you could do, as Martin said, you keep doubling, and then if it looks like it's second order convergence, you can do a Richardson extrapolation from the last two, and that's usually good enough.
Yeah, in the end, yes.
And I mean, at this point, here at 60 grid points, it's basically identical to the value which is dotted here with 120, so doubled. So we could say, okay, this is somewhere here does converge, or I could just take a threshold, say, okay, I accept a certain percentage of deviation from whatever is the very, very converged value, and then take all this, like have a barrier here, and say, okay, up from here on, it stays within, like, say, a 1%, a 5% error margin, right? Then I know, okay, everything above will, at this Reynolds number, be a sufficient resolution.
Yeah, so what we'd like to see is a log-log plot showing difference from something is going down like some power of
Okay.
grid spacing. And then I think everybody would be happy with that. But if you're saying that's not computationally feasible, then I think sometimes we do have to accept that.
But wouldn't you call this somewhat of a convergence?
There's this pre-convergence. You know,
Yes.
you have three regimes if you look at this.
Yeah.
Pre-convergence, so then when you have the oscillations, like then you have a pre-asymptotic range.
Yeah,
Then
where
you
it's
go to
monotonous.
the range, this is what Paul is saying, then you will see this power, and then you will run into something like round-off error problems. That is the post-asymptotic.
Okay,
range.
yeah,
Yeah, when this will flatten out.
okay.
But I mean, yeah, as Matthias said, this is not very high resolution, but this is in the pre-asymptotic state, or still.
Well, we can't really tell because of the way you plotted it. I mean, we really want to see it see error on a log scale.
Okay, yeah. Or to some value I say is the right value. Okay.
And if it doesn't do a straight line going to zero, then you can choose the right value to do the logarithm of the difference from.
Okay, yeah. I think even if you don't call it a convergence study, the point holds that if you just look at a couple of values, you might think, okay, I just take some resolution, looks nice, I'm close to the literature, but if you look at something different where you don't have the literature values and want to take this as a result, then it might be just wrong because you are not converged.
Yeah.
Yes.
I think we should wrap up the conversation. At least for now, happy to continue it afterwards. So, thank you.
Of course.
Okay, so changing title, we have that's what I felt like it was sent last night. Okay, so next up we have Florian Kozelbauer, who's going to talk to us about the exact non-local points of exam.
All right, there you go. Okay, so does that work? Can you hear me? Perfect. Okay, so thank you for the introduction. This is joint work with Ilya, and I try not to rush through the material, but I will fail. So the basic question we're asking is quite a fundamental one. Given a statistical kinetic model, is there a dynamically optimal self-consistent way to derive a closed set of equations for the macroscopic observables, right? So it's very, very old and basic questions in statistical mechanics. And the motivation for that is that we want to have consistency between physical theories, that is to say kinetic models and continuum dynamics, and we want to resolve certain inconsistencies or instabilities that arise from the Chapman-Enskog series. The second motivation is that we like to have optimal macroscopic equations for rarefied flows because we want to do analysis on them in numerics. And the third motivation ideally is to explain physical phenomenon of rarefaction on the effect of macroscopic observables and no longer on the kinetic level. This question dates at least back to Hilbert, who asked this in the context of statistical description of gases and continuum mechanics, and on a theoretical level that leads to the infamous closure problem, to which we will give an optimal solution. Okay, so first let me tell you what kind of models I'm considering here. I'm focusing here on linear kinetic models with a free flight operator and some negative semi-definite collision operator. And this will be derived as linearizations of non-linear kinetic models around some equilibrium distribution. So you could have a classical full Boltzmann operator with some collision kernel and some cross-section. You could have something like a Fokker-Planck operator, or you could have something like a quasi-equilibrium approximation like the BGK operator. So these are all covered by this theory. And what do I mean by the closure problem? Well, I mean that you take moments of your distribution function, of your kinetic distribution function, and what you get is you get some kind of a hierarchy of equations where at any order of moments, the higher order moments enter through this divergence through the free flight operator. So you get this infinite chain of moment equations and you don't know how to close them. So what do? Well, you have either an ad hoc assumption, depending on the system, how to close it. You have physically motivated closures, or you have some traditional approaches like Chapman-Enskog, where you make an expansion in your presumed small relaxation time or Knudsen number, and then you cut at a certain order. At leading order, you obtain ideally Euler equation, then Navier-Stokes, and for higher order contributions in epsilon, you get Burnett or super Burnett. And the problem is that depending on your collision model, you could get something like the Bobbilev instability of the Burnett model. Okay, so Navier-Stokes, if you go beyond Navier-Stokes, you might run into troubles if you do Chapman-Enskog. Okay, so what I tell you here is based on two ingredients, a slow manifold and spectral analysis of kinetic operators. I'll give you an optimal closure to your system. I'll tell you the structure of the hydrodynamics you get from that. And I'll show you an application to two model problems, classical model problems. Okay. First, what do I mean by the slow manifold? The slow manifold is an object in phase space, which is defined through a separation of timescales, and it attracts all trajectories in the neighborhood exponentially fast. And the exponential decay towards that object is optimal. That means the general trajectory to your kinetic model can be split into a projection onto that manifold plus an error term. And the error term decays exponentially fast with optimal decay rate. Okay. And because we're considering kinetic models, we have entropy. And entropy guarantees that any solution will converge to something like a Maxwellian distribution. So if you have a slow manifold like that, that's actually a global object. And here you see a picture of that for a toy model. The green curve is your slow manifold, and all the trajectories in phase space approach that manifold exponentially fast. Think about it, the trajectories in our case are distribution functions that are advected by the kinetic model, okay? So second ingredient, spectral theory of kinetic operators. So I won't go into details for that, just to give you some bullet points. So what we do is we slice our operator in frequency space, in spatial frequencies. And we know that at each wave number, our spectrum is stable. It better be because you have collision invariance and entropy. And then you can characterize what is called the essential spectrum. And the shape of the essential spectrum depends on the collision kernel. So if you're not familiar with operator calculus, the essential spectrum is basically corresponds physically to the fluctuations of the system. Okay. So on top of fluctuations, we have hydrodynamic modes. So for each wave number, we have a family of 4 hydrodynamic branches which bifurcate out of the origin. So you can think about those as spatially dependent generalizations of your collision invariance, and they move out of the origin and towards the essential spectrum. And for each of these branches, you have a critical wave number. So that's a pure operator theoretic property of these branches, but we will see that this corresponds actually to some physical property when we look at the hydrodynamics. Okay, that's a picture. So left is the essential spectrum, right is your hydrodynamic branches. And the connection to the slow manifold is that these modes, so each of these modes corresponds an eigenfunction in the kinetic space. And if you project onto these special kinetic modes, we get a slow manifold. So we're guaranteed that this manifold attracts all kinetic trajectories exponentially fast. And so the arrow that we make, if we define a closure on this object, is minimal. Okay, so it's the optimal closure you could get. Okay, so let's see how these closed hydrodynamics look like. Oh, sorry. So that's one more step to show you how we get the closure once we have the slow manifold. So we start with a kinetic model like this. Then we do a detailed spectral analysis on its linear part to obtain its slow spectrum, that is its hydrodynamic modes. Then we evolve these guys in time. So that's just a diagonalization. And then we change coordinates linearly on that object to obtain physical quantities. That is our macroscopic variables like density, velocity, and temperature. Okay. So that's how the equations look like. So they're formulated entirely in terms of macroscopic variables. On the right-hand side, you have a matrix with some differential operators. They only involve gradients and Laplacians, and the actual numerical coefficients depend on your collision model, so whether you use hard spheres or BGK and so forth. And then the most important thing probably is this guy K here, which is an integral operator. So you could think of this as a filtering process in frequency, something like a low-pass filter, which depends on a criticality parameter kappa, and physically that's linked to your Knudsen number. So depending on your Knudsen number, you include more or less frequencies in your rarefied hydrodynamics. What are the properties of this equation? Well, physically, it has the structure of a conservation law. So you have a matrix current from which it is derived that just corresponds to this spatial divergence in the order of moment equations. And then as a consequence of that, you get natural boundary conditions for vanishing fluxes on the hydrodynamic level, right? So I'm discussing kinetic boundary conditions towards the end if we have time. Okay, let's go back to frequency space, what that means. Well, in frequency space, as I said, this K operator is just a cutoff for a certain frequency range, which depends on your Knudsen number. And then the coupling between your moments, your macroscopic observables, is through these functions that depend on wave number, which we call generalized transport coefficients. And they're nothing but a frequency dissipation relation that couple the moments. Okay. As I said, the critical wave number, which is a spectral property, corresponds to a frequency cutoff of the dynamics, which means that you can resolve the hydrodynamics only up to a certain frequency to get a separation of timescales. Okay? And the most striking property, physical property of these models, of these optimal closure models, is the existence of entropy dissipation balance. So you have a wave number dependent entropy and a wave number dependent dissipation matrix, which guarantee that your dynamics are purely dissipative. In particular, any of these models, no matter which kinetic model you start with, they're guaranteed to be globally stable and hyperbolic. Okay. So if you compare that to other models like Burnett or Super Burnett, you could regularize them and make them hyperbolic afterwards, so do all kinds of stuff. But here, you're guaranteed to have that property a priori, no matter with which kinetic model you start with. Okay. So, oops, sorry. Here you see, or you don't. Now you see a comparison of these dissipation frequency curves for the BGK model. So the solid black line is the BGK model and the red dashed line is Navier-Stokes. And for small frequencies, so for small wave numbers, these coincide. You have the right asymptotics. That means we recover the Chapman-Enskog approximation. But for large wave numbers, you see considerable deviations in some of those guys, which account for rarefaction effects. And we will see that in the applications that these actually kick in. Okay. And one example is a very simple example, just to illustrate that these hydrodynamics are able to capture rarefaction effects, is a Knudsen minimum it's just a channel flow. It's two parallel infinite plates separated by a distance d. Keep the density constant, introduce a constant pressure drop along the channel. And then you're interested in the normalized flow rate independence of inverse Knudsen number, right? And intuitively, what you have is if you go to the delta to infinity as the fluidic level, you know that viscosity vanishes and you expect infinite fluxes. And if you go to the fully ballistic regime, you have no interaction between the particles and you have just a constant acceleration through to the pressure drop and you expect infinite fluxes as well. Okay, so it's just for the physics. Now, that's what is predicted by this optimal hydrodynamics. So bear in mind, it can only be as good as the kinetic model you start with, right? So if you want to improve, you have to improve your kinetic model at the same time. So the dots are the prediction from BGK is taken from Cecchiniani and Danieri. And the solid black line is the rarefied hydrodynamics, right? And you see that we're spot on at the minimum. We get the correct asymptotics in the fluidic regime, and we slightly overestimate the asymptotics in the ballistic regime. But remember, we never made a claim for that regime anyways, right? Because we're only limited to a certain range of wave numbers. So to give you, well, it's a little of a treat for this model is that you get all the quantities explicitly. You have formulas for everything. You don't have to do numerics. Solving the Knudsen minimum is as difficult as solving the heat equation then in Fourier space, right? So if you do harmonic analysis on the bachelor level, you can solve it now. You get everything explicitly, and you get excellent agreement, right? So that's from Cecchiniani, Danieri, and these are our results, and they match very well, okay? So let me give you another example. Another application is a light scattering experiment. What you do is you take a fluctuating gas and you hit it with a light ray, a certain frequency and a certain wave number, and you look at its deflections from the scattering, and then you measure the intensity and relate it to the expectation of the two-point correlation function of density, okay? And these curves look something like this. You get your Rayleigh peak, you get your Brillouin peaks, and if you increase Knudsen number, you approach something like a bell-shaped Gaussian type curve. And these are to give you some nasty formula, because I have to show one nasty formula per talk, it's the exact hydrodynamic fluctuations if you derive them for the general model, okay? And these are our results. So this is joint work with Candy Zhang from Hong Kong University, and this is an ongoing work. So what you see here is the orange curve is Navier-Stokes, right? The blue curve is the rarefied hydrodynamics, and the green and the red curve are the kinetic models SBGK and Shachov model. So here we're in the fully fluidic regime, and we see that they all overlap and you get your peaks, right? So if you increase your Knudsen number, we see that Navier-Stokes starts to deviate, right? It likes to be more bell-shaped already, whereas the hydrodynamics is very close to the kinetic models, okay? So if we increase further, we see that Navier-Stokes does something whatever, but the blue curve is still very close to the kinetic models, meaning that we really capture the kinetic effects on the level of hydrodynamics. Now, an interesting thing happens if we increase even further in wave number. So remember, we're not guaranteed, we never make a claim that the hydrodynamics should even hold true in that regime. What you see is that the kinetic models, they produce these spurious peaks. There is no Brillouin or Rayleigh spectrum anymore. But if you compare, which I'm not showing here, so you have to take my word for it. If you compare that to the DSMC, you see that you will see that the blue curve is actually closer to the DSMC than the kinetic model, which is interesting, right? But it's not that surprising because if you remember, we have a built-in filter in our non-local hydrodynamics. So we kind of like damp that out, and we're actually doing a better job than the kinetic model, okay? So let me give you a quick summary of what we did. Well, we presented a general technique, which we call spectral closure, which does the following. You start with a detailed spectral analysis. You calculate this low spectral manifold, which is associated to eigenspaces. You get an optimal closure operator on that manifold. And then from that, you get a physical model, you get a physical systems, which represents macroscopic description of rarefied hydrodynamics, okay? We've shown some structure of that model, which is a conservation law, it is globally stable, it is hyperbolic, and it has the existence of an entropy dissipation balance, and it comes with a set of natural boundary conditions. Okay. And I applied it to the Knudsen minimum problem, and we applied it to density fluctuation spectrum. Okay. And maybe let me give you some outlook, what we're currently doing and where this is heading. So one thing we're doing now with Candy is we apply machine learning to the generalized transport coefficient. So we take DSMC data, we know the structure of the hydrodynamics. We know that we cannot do better than those. Those are optimal, dynamically optimal. So the only thing we have to do is we have to learn how the coupling constant varies with wave number, right? So you can learn that from DSMC data, and that's almost done. So we're writing that up now. Another thing that is of relevance is how do these verified hydrodynamics interact with the boundary. So we take a kinetic boundary condition, specular diffusion with accommodation coefficient, right? And we incorporate that into the rarefied hydrodynamics. And then the solution depends on the accommodation coefficient. So what I've shown you here is a rarefied co-ed flow, where on the left you have a Knudsen number of, I don't know, 0.08, and on the, wait, that might be wrong. That might be, that should be 0.15, so about twice the Knudsen number, sorry for that. And what you see is that the Knudsen layer develops independence of the accommodation coefficient, which is consistent with the kinetic theory. And then, of course, there is extension to nonlinear kinetic models, because all I've shown you now is on the linear level. Well, mathematically, that's just the deformation of your eigenspaces, and you can do that with techniques like the slow spectral submanifolds as derived by Delayave and co-workers, or similar techniques. All right, thank you for your attention. I'd be happy to take any questions.
So maybe I'm old fashioned, but I don't know if you've ever thought of plotting the ultrasound dispersion relation, because it's what people used to plot.
Right. So that's with respect to spectra, right?
Yeah, with respect to frequency times your typical covariance.
Right. It's another way of depicting what we did here. Also, it will show similar things. You would get very good alignment, we expect, with the kinetic theory, and then.
But
Right.
in the kinetic theory, there are different views about whether you can get the saturation and dissipation rate from just doing a plane wave analysis, or if you need to do the boundary value problem.
Oh, right. So that could shed some light on this, actually, if you were to include that as another example. So to be honest, we're not that interested. Okay, you could do now one example after another and just show that you have good agreement and so forth. But we're rather interested in moving further to more realistic things like shocks and so forth. I suppose, yeah. Thank you very much.
Just, okay.
Today, we have colleagues from the University of Strasbourg talking to us about a fourth-order entropy stable lattice Boltzmann scheme for compressible flux.
So thank you for the introduction, and thank you to all of you for staying until the last talk. So this is a joint voice with Thomas Bellotti and Laurent Navoret from Strasbourg. So the outline will be, first I will do a short reminder of the vectorial lattice Boltzmann method. So it has already been introduced this morning by Megala. And then I will explain how to improve the accuracy up to fourth order. And then I will give you some numerical results. So let's start with the vectorial lattice Boltzmann. So the objective is to solve a hyperbolic system of conservation laws.
So here, for simplicity, I take a space dimension equals to 1, but there is no loss of generality in what I will say afterwards. So this, here you have a system of conservation laws. So where W is a vector of conservative variables, and Q of W is the flux. So here you have an example for the famous inviscid compressible perfect gas equation, Euler equations. So in this case, you have the conservative variables is the density, momentum, and total energy. And here you have the flux in 1D. You have a pressure law, and you have the sound speed that is given by this expression. So it is an example, but you can also consider magneto-hydrodynamics, Maxwell equations, and many other models. So for this, the vectorial lattice-Boltzmann method consists in approximating the conservative data by the sum of two vector distributions. So you have two quantities, F plus and F minus, and W is the sum of these two quantities. And the flux is approximated by the first moment of this vector distribution. So because it is vectorial, you need only one moment, and you will have enough degrees of freedom because you have a vector. So then the lattice-Boltzmann is always the same. So you have first transport steps of these two vectors. So you simply shift your vectors on the grid. And then you have a collision step where you will update at the end of the transport step your two vectors with a relaxation between an equilibrium and the data that you have previously on the grid. And here, if you want to have consistency with your initial conservation laws, there is no choice. Your equilibrium distribution is necessarily given by this relation. So you simply you take equilibrium here and here, you solve this equation and you get this equilibrium. So there is no choice. So this is an algebraic calculations. So here I will do some bibliography. And I think that this representation has been introduced a long time ago by, I think that is by François Bouchu at the end of the 90s. And I think that the first time it has been used in the lattice-Boltzmann framework is by François Dubois in 2014, and by Benjamin Graille also. And I will do some advertising of the work of my team. So since it's now 7 years that we are working on this kind of models. Okay. So as usual, so now we will do the same as what we do in the scalar lattice-Boltzmann method, almost the same, which we will do the same process. So the first process is that the kinetic data is abstract quantities. So we replace them by more physical ones. So we want to observe W, of course, conserved moment. And you have the non-conserved moment here in Y. And what I prefer, so usually the non-conserved moments are only this part, but I prefer to subtract the flux so that this quantity is naturally small. So I call it generally the flux error, but it is a kind of non-conserved moment shifted with the equilibrium. So in these variables, you can rewrite the lattice-Boltzmann, sorry? No, it's okay. So you can rewrite the lattice. Yes, okay. Okay, thank you. So it's a central moment. Okay, thank you. I know I have the good term, thank you. So if you rewrite this equation, so it's the same as in the scalar case, you rewrite the scheme in these variables, and then you can denote the transport operator in these new variables by t of delta t, and the relaxation operator by r of omega. And in this notation, a step of the lattice-Boltzmann algorithm is simply you transport your data and you relax. So it can be written in this way. Okay. So now this gives you a second order scheme. So it has been studied by Paul when in a paper where he described the lattice-Boltzmann method as a strong splitting. And what is important for me is that if you consider a relaxation parameter equal to 2, you observe that the relaxation operator is an involution or a self-inverse. So it's kind of reversibility. And if you take omega equal 1, it's a projection. Okay? So it is not reversible. You could consider it as an entropy dissipative process. So this simple remark can be made much more rigorous. So if you replace your relaxation parameter, if you make your relaxation parameter depends on the data, it is possible to make the relaxation operator still entropy conservative, exactly, and also self-inverse. And it is exactly, so the technique is the same as the one that has been developed by Ilya since a long time ago. And it was presented this morning. So you can extend the idea of Ilya to the vector case. Okay. So then, so you can construct a lot of entropy conservative scheme now, because the transport step is entropy preserving, and the relaxation step is also entropy preserving and self-inverse. So for instance, my problem with one of the difficulties is that when you look at the lattice-Boltzmann method, you only have transport relaxation. It doesn't look like a strong splitting. You have to do some manipulation in order to transform it into a strong splitting algorithm. But what you can do, you can write what is called a palindromic scheme in this way. So you chain several operators with a symmetric in time, in a symmetrical way in time. And with this scheme, you get a scheme that has this property. So it is called time symmetry in the geometric integration community. So it satisfies this, that if you reverse the time step, you get the inverse of the lattice of this modified lattice-Boltzmann operator. And also it is very important that if you take a time step equal to 0, you have to get identity, the identity operator. So with these two properties, necessarily you get a second order scheme in time. By construction, this gives you second order accuracy. Okay. What can I say? So an important point here is that when you write this, you can still use the lattice-Boltzmann trick, which is you can shift your data exactly on the mesh by taking a smaller grid step. Okay. Okay, so I got so this will be the basic brick of my scheme. And now what you can do with this basic time symmetric brick is that I will speak of this later on. No, sorry. So now that you have this basic scheme, you can study it by a Taylor expansion. So if you perform a Taylor expansion, you can compute the equivalent partial differential satisfied by your scheme, and you get this. So it's there is no Chapman-Enskog analysis, no hypothesis on the smallness of the central moment. And if you just perform a Taylor expansion and you get this equation. So what you observe in the first line, you have your initial system of conservation laws that you want to solve. And what is funny is that on the second line, you get the evolution of the flux error. So you see that they are uncoupled. I repeat that you don't need to assume that y is small. And you also see that the wave for y and w moves in opposite direction. Okay, so this is the analysis, the consistency analysis of the basic brick. And now what you can do is that you can compose this basic brick with what is called the palindromic composition of this form. So you chain your basic brick k times, then you have a central step with a different time step, and then you, again, k time in order to have a palindromic symmetric in time composition. And then it can be shown, it is explained in this paper, for instance, that if you have this relation between the central time step and the external time step, then your scheme is fourth order in time. So there are some questions here. These two relations here impose that beta is negative. So it means that you will chain the basic brick several times, and then you have to go back in time sometimes. Another important problem is that generally alpha over beta is not rational. So it means that you will not be able to shift exactly on a structured grid, apparently. But actually, we are very lucky because if you take k equal 4, then you observe that the solution of this set of equations is rational. So in the end, you can end up with a true lattice-Boltzmann scheme with only shift on the grids. And about negative time stepping, for the moment, I am not too annoyed because I'm writing an entropy conservative scheme. So if I go back in time, it's not a problem. What time is it? Okay. So a summary. So here you have the traditional lattice-Boltzmann method. So you advance by small time steps. And you can compare with this new method here, where you advance, you have 4 steps made of 4 sub-steps. Then you go back by a twice larger time steps, and then you go back, you go again in the same way. So it's a little bit more jazzy than the usual method. Okay, so if you count the cost, for the classical lattice-Boltzmann method, you would have 24 steps. Here you have to go back in time sometimes, so it's a little bit more expensive, but it's fourth order. Okay, so now let's go to numerical results. So the scheme that I presented is entropy conservative, so it's really no dissipation. And of course, if you have shock waves, you will have a lot of oscillations in the shock waves. So it's important to have some dissipation mechanism, but you also want to preserve fourth order in smooth regions. So what we have found is that if you end your basic brick with a simple projection, then you keep fourth order. So if you measure the order of the scheme, you observe that it is still fourth order. And if you put the projection inside this brick, it will not work. You have to do it only at the end. And then, as before, you do this composition here with a negative time step in the middle. And if you want to see more details, you can see our preprint, recent preprint. Everything is explained here. Okay, so we can check. So now some numerical results. So we have done, so these tests are done with the Burger's equations. So here you have the basic brick, you observe that it is indeed second order accurate. And then you have this scheme is a ideal entropy conservative scheme. And this one is when you project at the end of the two lattice-Boltzmann steps. So it's fourth order. Then a very important aspect is that because the scheme has very small dissipation, it's very important to ensure that it is stable in long time. So as it was presented this morning, you have a spectral properties. If you take omega equal 2, generally it will not be stable in the nonlinear case. So it's important to check this. So here you have we have programmed the method for the shallow water equation, which is another hyperbolic system of conservation law. So if you take the classical omega equals to 2, then in the long time, it becomes unstable, and then your scheme is exploding. But if you take the adaptive omega with the entropy conservative scheme, then it is stable in the long time. And here you have, we measure the evolution of the kinetic entropy during the computation. It is exactly conserved as expected. And then finally, we were able also to, so here you have an example with the Euler equations in 2D. So the method can be extended to 2D. Then you will use a D2Q4 scheme multiplied by the number of conservative variables. And then you end up with this kind of scheme of results. So here you have a 1000 times 1000 grid, and here the double grid. And you see that it is you have a sharp shock waves. They are well resolved. You have anyway, there are absolutely no shock limitations or muscle method or nothing. So of course, you still have some slight Gibbs oscillations, but in this case, the projection step is enough to damp the oscillations. And when you refine the mesh, things are going okay. Okay, so I come to my conclusion, which is that, I've presented you a fourth order lattice-Boltzmann method for hyperbolic conservation laws. There is also a full entropy stability analysis that is available. And we are currently working on the extension of the method with boundary conditions. Thank you.
That you use when you solve the Euler equations is no more vertical due to this R1 at the end of the.
I agree, you're right, but anyway.
So there is yes, there is a non-trivial theorem saying that if you replace P minus one basis P of minus delta T over P, you still have the same property.
Yes, but here it's not. So the time symmetry property is not true anymore for this operator. I agree. But I think that I have not analyzed this precisely, but we think that it is still fourth order because it's when you are on the slow manifold, when you are on equilibrium, then you have this property, but it's respected on the equilibrium variables. And here, what I had not time to say everything, but if you remove this and if you take the exactly entropy conservative operator, you can have it is not necessary to be at equilibrium during the computations. And you got a fourth order method. But if you add this, and if you start far from equilibrium, you are no more fourth order. If you want to be fourth order, you need to start at equilibrium. Is it?
So maybe another way to think about that is that the evolution keeps you close enough to equilibrium that the
Yes.
projection doesn't.
Nothing. It doesn't. It has a small effect that you can see on the oscillation in the shock waves, but it doesn't break the order. Yes, you're right. So of course, at this scheme, in all the internal time steps, you are second order. You observe fourth order when you arrived here. Yes, but you can use it as a second order approximation everywhere. If you really want to observe fourth order, then you have to go to.
Then you have like we're lucky with the K. How does it go on for higher order? Are you still lucky for K greater?
No, I don't think so. It's a very special case, and actually I worked on a palindromic method 7 years ago, and I stopped to K equals 3. And I just discovered a few months ago that if you go to K equals 4, then of course you can still use lattice Boltzmann. But it was a discovery It was a very stupid discovery, but I don't know why. If you go to the literature, it describes up to k equals 3, and then nobody cares. But if you go just one step further, then you get a huge property. And I think maybe that it will be possible to find. I'm not a theoretical number analyst, so I cannot. I don't know. Maybe.
If there are no more questions, then we should thank Pete and all of our session speakers.
Thank you.
Yeah. And actually,